Hi, this is Jeff from the Ozark Mountains in Missouri, USA. Well, you've probably already guessed by the title that this video is about this guy. It's a Sharp PC-1500A with a turbo switch. A turbo switch, well, yes, that's what this little guy is here. You'll notice it has an S and L on there, which might seem funny, but this was done in Germany. So the S was for schnell, which is fast, and the L is for langsam, which is slow. Seems a little odd from an English perspective, but it makes perfect sense if you speak German. So what we'll do in this video is we'll try this guy out. We'll run some programs, calculate pi to like 20 digits, check the speed difference between the two. We'll see how this works with accessories such as the CE-158X and the flash and RAM expansion board. We'll do some load time testing, and then we'll take it apart to see how it's made. So without further ado, let's get started. Thanks to PCBWay for sponsoring this video. They not only do PCBs and flex PCBs, they also have 3D printing service, injection molding service. They do CNC machining, sheet metal fabrication. They also have a thriving maker community where you can share projects and check out what other people are doing. For your next project, head on over to PCBWay. I've got the CE-158X connected. I'm going to use the USB connection, which you can see just here. For this file transfer, I'll turn it on with the switch here on the side. I'm going to turn the computer on. That procedure is just the same as with the original Sharp CE-158. Then I need to tell it to use the USB connection, which is U1. The RS-232 normal serial connection is U0. So to set it to U1, we want to do set dev CICO redirects cassette input, cassette output to the serial port, or in this case U1. And then we just type in U1. And the USB port is automatically set to 19.2 and all the handshaking and stuff, so you don't have to worry about that. Now I'm going to do a C-load, small a for ASCII, and hit enter, start sending the file. There we go. One other thing I forgot to point out is I have our turbo PC-1600 set to L, which is slow, if you'll recall in German. Now I'm going to go ahead and load the same Pi test program up on the other computer. I'll run them both at the same time and see what the difference is. The bottom computer is our PC-1500A stock, no memory card, nothing else added, except for our switch over here set to the schnell or fast position. The top upside down PC-1500A is a bone stock. Same thing, nothing added. They both had the same ROM version, which is what you see here, A04. And I have a little stopwatch over here, so I'm going to hit run on both. See if I can do this upside down. Okay. We're going to calculate pi to 20 places. I have 20 entered on both. And see if I can press 3 buttons at once. Yep, they both say busy, so they're both running. And we've got our stopwatch running. Okay, in turbo mode, it took 1 minute 44 seconds, which is 104 seconds. In normal mode, it took 2 minutes and 43 seconds, which is 163 seconds. 104 divided by 163, which I conveniently have plugged right in here. So it's about 0.638. In other words, turbo mode is about 36% faster. Which is not too bad. Now, the clock speed in the PC-1500 and 1500A is 2.6 megahertz. That's divided internally in the processor to 1.3. In Schnell mode, fast mode, we're doing 136% of that. So if we take 2.6 multiplied by 1.36, we get a new frequency should be around 3.54 megahertz. 3.54 megahertz. Now when we take it apart, we can measure that, see how close we are. And interestingly, that is very close to the NTSC color burst frequency. So I don't know what they used inside of this thing from Germany. They probably did not use an NTSC color burst crystal. Even though they were super cheap at that time, they just wouldn't have been that common in Germany. But it's interesting. Now, let's see if we can load programs on this guy with our CE-158 in Schnell mode. I suspect it will work, but let's find out for sure. Alrighty, we've got our CE-158X hooked up by the serial port. Our PC-1500A is set to Schnell fast mode. And we'll zoom here on the screen. I actually did this test already, but I forgot to press record on the camera, so we'll just do it again. So we'll need to set up the serial parameters here. Set dev CI, CO redirect cassette input and output to the serial port. Then we're going to set COM 38400. We're going to go as fast as our 158X will let us. Normally we can't do this because the 158 or PC-1500 is doing a lot of data processing rather than just moving data from one to the other. It's got to massage it as it puts it in the memory, etc. And then we're going to go out stat 0, which sets the handshaking. And then we can go cload bat.bas. This is a beta escape program that I use a lot for loading and saving testing. And then I will hit enter, click send on the computer, and we're done already. It's less than 2K, so not a big deal. We're in program mode, so we'll do list. And I am so used to looking at this program by now, I can kind of go through here very quickly. Going into the data statements, everything looks good. And we can check it out by hitting run. This is very difficult at the faster speed. Okay, so we can load 38.4 at least with the small program that is already tokenized. So now I don't have any additional memory in this. There's only about 6K in here. So to get a good test with longer programs, I'm going to go ahead and put in our flash/RAM board and get that configured, and then we'll come back and we'll try to load a large ASCII program and see what happens. Got the memory card installed and CE-158X hooked up. We're using the serial port this time. And we'll zoom it in here. If we type in mem, you can see we've got about 22K available. And we'll go ahead and set up the serial port for loading. Set COM, we'll do 38400 again. We're going to set device CICO to redirect cassette input and output to the 158X. And then we'll do out stat 0, turn on the handshaking. Okay. And we are going to load a 15K ASCII file. Okay, now I'm going to start the stopwatch as I hit send on the PC. Okay, I got a little click happy there, but it took about 2 minutes and 45 seconds to load the 15K ASCII file at 38.4. I'm going to go ahead and reload that at 19.2 so we can compare the difference, but I won't make you suffer through it. I did some more load time testing. With the original Bethescape program, which is tokenized basic, at 38.4, it took between 2 and 3 seconds to load. At 19.2, it took about 4 seconds to load, so not a big difference there, but it was only about a 2K program. The Hanoi.asc, which is a bunch of programs tacked together, it's about 15K. At 38.4, it took 2 minutes and 43 seconds. At 19.2, it took 2 minutes and 48 seconds. I was really surprised by this lack of a difference. The problem with ASCII programs is that it's just like you're typing the program in. When it gets to the end of the line, it has to tokenize that line, which takes time. At 19.2, I find about a 300 millisecond delay after the end of each line works well. I can probably reduce that for 38.4, but this is an apples to apples comparison, showing that even though we're transmitting twice as fast at 38.4, it's not doubling the speed that we're loading the program because it takes time in the computer. So if we're able to reduce this, that end of line delay, we could make it a little faster. I'm popping up that settings screen here. For CoolTerm, you notice that on the top where I have checked, it says use transmit character delay. 1 millisecond works great for 19.2. I tried dropping that, and it does make a difference. We'll get to that in a second. And the transmit line delay is after each line. You only need to use that for ASCII programs. And again, about 300 milliseconds works pretty well. And that's all dependent on the length of the line, the instructions are in a line, how long exactly it takes to tokenize. The same program, Hanoi, but in tokenized basic, since we don't need that big 300 millisecond end of line delay, but we still have the 1 millisecond character delay. At 38.4, it took 30 seconds. At 19.2, it took 31 seconds. If I drop that 1 millisecond end of line delay to 0.5 milliseconds, that dropped it down to 27 seconds. The data by itself would only be about, let's say, 9 or 10 seconds. So we're spending 3 or 4 times as long waiting or delaying as transmitting the data. So a lot of problems with these old machines is it takes them so long to process stuff. It doesn't really matter how fast you can get the data there. You wind up waiting a lot. So to summarize, for ASCII programs, that end of line delay really dominates everything. If we can adjust that, which we probably can adjust that down, we can make transfer at 38.4 a little faster. For basic programs, the character delay is 3 to 4 times the time it takes every byte to get there. These old UARTs and these things hold 2 bytes. They have the byte they just received and the byte they are currently receiving. At 38.4, the bit time is about 26 microseconds. So a full 8-bit byte, one start bit, takes about 260 microseconds. So with a 1 millisecond delay, we're waiting about 4 times as long between bytes as it takes for them to come in. And that's, just how it works on these older machines with slow processors. but it's interesting nonetheless. It's interesting that we're fast enough to go at 38.4 now with it in turbo or Schnell mode. And with some tweaking, we can probably reduce these times even more, adjusting these delays and still come up with something that's reliable and faster. Now, I think we'll get into taking the computer apart and seeing how they did it. I thought before we take the computer apart, it would be interesting to kind of theorize about how they may have done this speed up. This is the schematic for PC-1211. It shows an oscillator right here, the loading caps, and a resistor across it. Happens to be 1 meg in this case. So that resistor being there tells me that this is a ceramic oscillator instead of a crystal. They both do the same thing. The crystal is more precise, more expensive for something that's not quite as demanding. The CPU running on a pocket computer at an exact rate is not that big a deal. So the less expensive ceramic oscillator is fine. We have an example of one of those here. These can have 2 pins or 3 pins. They're usually in a plastic package. And we have the loading capacitors right here. And this is a Sharp PC-1251 board. A crystal, on the other hand, can come in a can that looks like this. It can look like a little flat can, a cylindrical can, much larger, but they're in a metal can. And these 2 caps are the loading caps for the crystal. This is an Epson Mosu board, the main board out of an HX20. So how would they speed it up? As I recall, on these ceramic oscillators, if you play with the values of the loading caps, you can change the speed quite a bit. For a crystal oscillator, changing the value of the loading caps does not make that much difference. You kind of use that as a fine-tuning mechanism. So rather than trying to change it by 30% like this guy did. So we'll go whiteify again. And take our batteries out. I believe all these cover screws are the same except for these 2 guys in the battery compartment. Or 3 guys in the battery compartment. And I would not be shocked opening this up if there's some bodge wires in here or the moldy candy bar. On the early PC-1500s, there's a lot of bodge wires, and it does seem they got reduced as they matured. Okay, that is a different screw. I wonder if that was because of the switch in there, if that's how they all are. I don't remember. Okay. So the case splits along this back line here like this. And we need to pop it apart like so. Okay. Oh, no bodge wires. How about that? So, yeah, so we have no bracket down here for the screw to go into. This one did not have the moldy candy bar looking thing up in this corner. And we have 3 wires from the switch running down under the board. Okay. Let's zoomify here. And you'll note this little cylindrical metal can right here. This is the real-time clock crystal. Okay, so we need to remove some more screws. Now these 2 are for the 40-pin connector. Those don't need to come out. They've got them glued down. So this one needs to come out. This one hiding under the wires. What's interesting is it uses the real-time clock crystal for time, which means that our turbo modification doesn't affect the timekeeping. I don't know how many programs actually made use of the timekeeping or the real-time clock, but it's an interesting feature for a pocket computer of this era. It's always a little tricky. Oh, here, let me whiteify this for you. You couldn't see all those screws I was taking out, could you? You got to get the 60-pin connector out from under this hoop. Kind of tip it just right, hold your mouth just right. Okay. Here is our fancy modification. Let's zoom in on that guy. Zoom. Oop, blurry, blurry. Back up, back up, back up. Okay. So this is the original oscillator. I know that because I took some pictures of other ones I have taken apart. And they pulled one pin on that, ran it up through the white wire to the switch. They've got a 4 megahertz crystal here with one leg on the green wire, and then they both share a common wire here. So it's switching between oscillators basically, using the same load resistors, or the load capacitors rather, which might be these guys just here. You can't see those. These guys here, I think, are the loading capacitors. So that's an interesting way to do it. Having big flying leads like that on the crystals is not the greatest thing in the world to do. It obviously works. Can it cause problems? Yeah. You're adding some additional loading on these oscillators they weren't designed to take. It's held up well over the years, though. So that is quite curious. And they, tape the wires down. They try to do a good job. Yeah, given the what was available to the home experimenter at the time, this is probably a pretty good solution. I don't know how many of these were made, but it's quite an interesting task. So it's interesting. This is a 2.6 megahertz crystal, and this is 4. So yeah, this gets reduced down to 1.3. I calculated that the effective clock speed is about 1.75 megahertz instead of in turbo mode, instead of the 2 we might expect from this 4 megahertz crystal. But we can measure that just to see what the actual clock speed is. Well, it was rather interesting to see how this Turbo PC-1500A was made. Given what was available to the home, experimenter, somebody that was making a few of these on demand, they did a pretty good job. Those flying leads on the crystal's not the best thing in the world, but I'm not sure what else you would have done back in the day to get a selectable speed out of something like this, and it definitely does work. The speed that I calculated that it was running at based on the program running was a little slower than the actual. I guessed about 1.75 megahertz, and it was actually running at 2 megahertz, which is interesting. So it's quite a decent speed bump from going from 1.3 to 2 megahertz operational speed. The crystal speed is twice that, remember, 2.6 and 4. So I've been chatting with a friend about this, and we've been talking about, you know, how could we do a modern version of this without the big ugly switch on it? Maybe something that you could poke to a certain address and it would change the speed. So let me know if that's something you might be interested in. It would require tearing apart your precious machine, taking out the original oscillator and soldering in some wires. But it shouldn't be destructive. You should be able to revert it back to the factory condition fairly easily. So let me know about that. It's just be something fun to do. So thanks to everyone who helps support the Hey Birt channel through Patreon and other means. That's greatly appreciated. And until next time, bye.